Okay, here we're going to look at the sine wave now in more detail, and again just sort of zoom in on the parameters that are specific to a sine wave. First thing we should do is just sort of understand where a sine wave even comes from. It is just the y values as you rotate through a Cartesian plane. So let's do this. If we take a rotational, just a circle, right? Let's try to draw a circle here. All right. And as I rotated, I think you already understand, right? There I'm at 0 degrees, and when I get all the way around, I'm at 360 degrees. You know, when I'm 1/4 of the way around, I'm at 90 degrees, right? Here I'm at 180. Here I'm at 270 degrees of rotation. Okay. And look at the y values. I know it's pretty ugly looking. But look at the y values grow. They start at 0. And actually, let me do this for you too, because we're going to plot this out then. Starting at 0, right? So, and then they grow, right, at a sine rate. I mean, this is growing and then shrinking, right? And that, by the way, that growing is this, growing, right? Then shrinking, okay. That was the first 180 degrees, so it grows and then shrinks. And I know the scale is a little off, but basically, and then it grows again, right? But now in a negative direction, right? So it's growing and then shrinking back down. So again, it grows in a negative direction and then shrinks. Yep. Or another way you could look at that is we just took our two halves of our circle, right, and sort of unfolded it in a line, right? I mean, I took this half of the circle, and if this was drawn to scale, I mean, this half is the same as this half, and then this half is the same as this half. So here I've just taken that rotational drawing and put it in a line where it happens in time, rises and falls, rises in negative direction and falls. So either way you want to look at it, translating those y values or just unfolding the circle, just take the bottom half and unfold it in time. I don't care. But understand that that's really all it is. And here we can put the degrees in here. This is why we call this 0 degrees, 90 degrees. Here I'm at 180 degrees, right? Here I'm at 270 degrees. And here I'm at 360, well, back to 0 degrees, really. Yep. Okay. And this is the period of the sine wave, is the time it takes to go through a complete cycle. And we could put some times here just for our example. Let's just say it's 4 milliseconds to get through there. So all the way to 360 or back to 0, right? Let me put some times in here. This could be 4 milliseconds to get all the way through one cycle. So halfway through, right, 2 milliseconds, right? This is time 0. At 1 millisecond, I'm at 90 degrees, right? 3 milliseconds. All right. So period for a sine wave it's the same as for any wave. It's the time it takes to get through one cycle. Frequency is still the same as 1 over the period. That's how many cycles happen in a second. Once I know how long it takes to complete a cycle, I know how many will happen in 1 second. That's the inverse relationship of period and frequency. There is no pulse width and space width to a sine wave, but let's put that here. Let's see, no pulse width, nope, no space width, nope. However, what we do have for a sine wave is called phase angle. We want to know sometimes where we are at in the sine wave. So, you know, for example, am I here? Am I here? Where am I? Where am I in this sine wave? And it's true, I could specify it in terms of time. I could say, well, you are at, let's pick something, you know, you're at, I'll say 0.4. Let's pick something like 0.4 milliseconds, okay? So that would be a thing that we might want to know. So let's do that. Let's put it in here. I'm just picking a random number. So at 0.4 milliseconds, let's say I'm looking for that time of interest, and I can look there with my scope because I can measure time with my scope. So I'm looking right here. And we'll pick this as a point of interest and do a couple things with it. Now there's a couple things I'm kind of interested in. 0.4 milliseconds is what we would call little t here, the time of interest. So let me break that out. It's getting a little messy in there. That's the time of interest. This is an instantaneous voltage that occurs at 0.4 milliseconds. So I might want to know that too. And oftentimes, rather than talk about this point in the wave in terms of time, in terms of 0.4 milliseconds, I might want to talk about it in terms of where am I in terms of the angle, the phase angle. So that's a question mark I might have. Because here, this is the Greek theta. What is the phase angle? The reason we like to talk about it in terms of angles is if I told you in a sine wave that I'm at 0.4 milliseconds, does that tell you where I'm at? No, not unless I tell you, oh, by the way, the period for this wave is 4 milliseconds. So I actually have to tell you two things. If I'm trying to convey time, points in time, I can do it, but it's not as easy as just telling you where I am in terms of phase angle, like degrees, because I can tell you, once I calculate this, I can tell you where I'm at. Now I can see I'm a little less than 45 degrees, right? Because 0.5 milliseconds would be 45 degrees. But that's why phase angle is useful. I'd rather talk about where I am in a sine wave in terms of degrees. Then I don't have to give you all the information on, the period and that time, and then have you calculate it. So let's show you how we do all this, because I think these are some important things that we look at and we say to ourselves, we might be interested in instantaneous voltage or phase angles. So how do we get those? And let's take the phase angle first. I think we developed this in a previous video. We hinted at it, but it was towards the end of the video. It's pretty easy to calculate phase angles from time. So let's do that over here. Wherever you are in time, that time of interest out of your total time for the period, that's your period there. It's going to be the same as where you are in terms of degrees out of 360. I think that's pretty obvious, isn't it? Wherever you are, this time of interest is 0.4 milliseconds out of 4 milliseconds, right? Well, I can see that's where I'll be in terms of degrees out of 360. Okay, so you just solve for it using this. But this is a formula you just always want to have ready in your head, because we use that all the time, because your scope can just measure time. It doesn't measure degrees. You have to always be calculating that and converting to degrees. So your scope skills get you time measurements, but then you have to use this formula or this what do you even want to call it, a formula? Probably just this relationship, right? This ratio. Let's see where our phase angle is here that we picked of interest. So 4 milliseconds, right? I mean 0.4 milliseconds is our time of interest out of 4, right? And so we could take bring 360 over, right? It'd be this, right? It'd be 0.4 out of 4 times 360. There's our phase angle. See, you get to say things like phase angle now. This makes you sound smart. 0.4 divided by, and then times 360. I can do that quick, right? All right. I think I know it already, but let's just check it. Yep. That's 0.1 times 360. It seems like we're at 36 degrees. Unless I did it wrong, but hopefully that's right. Okay. So phase angle is 36 degrees, the point of interest. Then we might ask ourselves, what is the voltage? This instantaneous voltage here? We might want to know that. So let's figure out how we can calculate, that. Okay. And this is another common thing we'll do with sine waves. Well, now that we know the angle of 36 degrees, let's come back over to our Cartesian plane. So let's look here. So our angle, I'll try to draw 36 degrees. Okay. Is here. And our instantaneous voltage that we're looking at, it's this right here. It's this amount right there that we're looking to get. So we can use trig. We can use trig functions to get this. You need to see one more thing. That, I mean, this is the unknown that we're trying to get. So it's the side opposite the angle, right? And then, can you see that this radius here is, when we swing all the way to here, you can see it, I think. Swing around to 90 degrees of rotation. Do you see that radius is our peak voltage, right? It's this right here. Okay. So we can definitely use trig because the sine function, I mean, trig functions are just ratios. Somebody figured out a long time ago that for any given angle, in our case it's 36 degrees that we're using here, but for any given angle, it doesn't matter the specific size, the ratio of one side to the other for a given angle will always be a constant. It'll be the same. You know, so in other words, if this is our 36 degree angle here, the ratio of the opposite side to the hypotenuse is the one we're looking at. But there's ratios for all sides, right? I mean, there's this ratio from this side to this side, or this side to this side, or this side to this side, and they all have names, right? I mean, that's the sine there. The cosine would be the ratio of the adjacent side to the hypotenuse, and so, and then of course the tangent would be what, the opposite over the adjacent. So there's a quick little trig lesson for you, but I wanted to say that this ratio never changes, no matter how the actual numbers of the sides are. Whatever the size of the triangle, as long as the angle is the same, the ratio is the same. So that's very useful. So what happens is that ratio that never changes is for the opposite side over the hypotenuse, this over this. That's what we're looking to solve for in our case, because look, it's It's this that we don't know. We know the peak voltage. Well, we don't. I didn't put it in my example, did I? So let me put it in there. Let's just say it's 10 volts peak. So for a sine wave with a 10 volt peak, we might ask ourselves, what is the voltage at 0.4 milliseconds? Well, and it's also a 4 millisecond period and a 10 volt peak. Do you see how the parameters all play together? So I've got a 4 millisecond period, a 10 volt peak. I want to know what the voltage is at 0.4 milliseconds. That's also, so I have to convert that because I can't do trig functions on time, but I can convert that. I know what that is. That's 36 degrees of rotation. I'm at the 36, the phase angle I'm at is 36 degrees. So then I can ask myself, what's the instantaneous voltage for a sine wave that has a 10 volt peak? What is its instantaneous voltage at 36 degrees? And that I can solve for because these trig functions, the sine of the angle is, well, in trig, it's the ratio of the opposite over the hypotenuse. For us, that means the opposite side is the instantaneous voltage. Okay, this is the opposite side of our little triangle that we see here forming. So the opposite side is right here. And the hypotenuse, if you can see it, is the peak voltage. I mean, rotate this all the way to 90 degrees and you see that they're one and the same. So the radius here is the peak. It's also the hypotenuse of this little triangle. See that? It's right here. So that is our peak voltage. And that relationship works out really well for us. So we'll be using this formula quite a bit. The sine of the angle equals V instantaneous over V peak, and lock that one in. That's another one that's big in the AC course. Of course, when you were actually using it to solve for instantaneous voltage, it turns out to be whatever angle, whatever your phase angle of interest is, take the sine of that, times it by V peak, right? I'm just rearranging it algebraically, and poof, out pops the instantaneous voltage. And we'll see what that is in a minute. So if you've done trig before, or if you haven't, but you got to get your calculator out, you got to find that button that says sine on it, and you're going to put in some keystrokes like 36 degrees. Make sure your calculator, by the way, has to be in degrees. So make sure it's in degrees, not radians. Then you're going to punch in, and I can help you with that when we get on site. But it's something that, of course, is important, what mode your calculator's in. So you're going to punch in maybe 36 and then hit the sine button, and it'll give you the sine of 36 degrees. Because remember, that number that it's giving you never changes. It doesn't matter what the actual sides of the triangle are. The ratio of the opposite to the hypotenuse is the same number for a given angle. So we know the angle is 36 degrees, so the calculator tells me when I when I do the sine of 36, it gives me a number. So I took the sine of 36 degrees, and the number that the calculator gives me is 0.5. Oops, let me get this. I'll round it, but maybe I'll go a couple significant figures. Let's see, 0.58. I'll round it to 4, 4 sig figs maybe. That's the ratio of this to this for this degrees. It's also the ratio then of this to this, right? Oops, what did I do there? Which isn't drawn quite to scale, but we'll have to live with that. So I can see I'm a little more than half, right? A little more than half. Well, it shows up pretty good over here. So when I do the sine of 36, it's telling me that this length is going to be a little more than half of this length. So so that's it. I mean, we'd have to our drawing is a little bit to be desired here. This doesn't look like a little more than half of this, does it? That's okay. The triangle does. All right. So what we're doing is the sine of 36 degrees in my calculator, and you could try different calculators. You got to know your calculator, how to punch that in. For some calculators you got to put the number in, the angle in, and then hit the sine button, right? So you have to figure that out. If you hit the sine button and then the number, that might not be it. But it depends what type of calculator you have. The peak voltage is 10 volts. So you can see we're just taking and solving for instantaneous voltage. So it looks like 5.878. And I can go to just 3 sig figs, I don't care. 5.88 volts is my answer. Now, being in the AC course, it's kind of not clear enough to just put volts. What is that? I have to remember to always include the subscript. Because is it 5.88 volts peak, or peak to peak, or average, or RMS, or instantaneous? So this is an instantaneous voltage for 36 degrees. Yeah. So we have our answer there, and it should be reasonable. It looks reasonable, if you're heading up, at this point now. Like I say, we didn't quite have this drawn very well, but you should be about a little past halfway towards your peak value, towards your peak voltage. Fix that up a little bit. True, that's Sine. Okay, so there we go, and let's see, get that over there. So two very important formulas, two very important relationships. Let's see, what other parameters we need for the sine wave. Average and RMS, we can talk about those. Sine waves can have offset. We will probably not be getting into much of that at all. The book does not, but it's possible. You can add offset to a sine wave. In other words, it will not be centered on 0 volts then, and that's a valid thing to do. We do not do that, I think, in any of our experiments. We don't need to, but just so you know, it's possible. But let's talk about maybe V average, VRMS for a sine wave. So overall, I guess if we aren't going to add offset to a sine wave, I think you can probably see, I'll draw it over here, that if half the time it's there and half the time it's down here, overall the full cycle average is 0, right, for a sine wave with no offset. So full cycle is 0. Simple enough. And obviously that's something we're not going to be that interested in. It's pretty simple. But there is another average, and that is it's used a lot with sine waves, and that is the half cycle average. Or in other words, it's sometimes of interest to say, okay, I know overall, I'm up here and down there, so overall the true average is 0. But let's just take one of these halves at a time, because again, the load doesn't care which direction current's going, so it's going to be looking like it's getting this and then, well, current's going the other way, but it'll get the same, essentially the same effect, just current going the opposite direction. So the question becomes maybe, what is the average of any half cycle? So the average of a half cycle comes in here, and a number, well, it's actually going to be, I'll give you the very specific ones, but I find it easier just to remember a number. 2 over pi, I think, yeah. Which is approximately 0.637 of the peak. So whatever your peak voltage is, your average voltage, I should draw this a little bigger. Your average voltage for a half cycle comes in a little over half of your peak. This number is probably easy enough to remember, or if you want to remember, this is more accurate, the 2 over pi. I don't care which you memorize. Okay, and then let's draw that just a little bit bigger because I feel like we're going to need more room. Okay, so let's get back to okay, that's better. So V peak, of course, is here, and then V average half cycle, I always have to keep, emphasizing, it sits around there, the average of any. And, I think you can see it makes sense that it's a little over half because of the sine function itself rises quickly and then more slowly. So it's rising rapidly and then more slowly. So if you think about it, you spend a little more time in the upper parts of the voltage of the sine wave because it gets there quickly and then slows down. So there's more time spent in the upper half of the voltage. So that's why we have this average, half cycle average would be a little greater than half. All right, then we have the RMS to look at, and let's get that in here. If you remember, it's still, again, the root mean square, so it's squaring all the values and then averaging them and then square rooting them. I don't know that it's as easy to see as in a rectangular wave where you just have 2 voltage levels to square. Here you got to square every point on the wave. But the bottom line is you are going to look at an RMS value, and it can be full cycle now because the squaring takes care of the fact that the voltage goes positive, negative. Doesn't care about that. It wipes that out. So RMS, we don't have to specify full cycle or half cycle, but the RMS, let's drag this up a little bit, is again, you have your choice. It's whenever the actual number is 1 over the square root of 2 times V peak, but easy enough to remember. I think most people just memorize 0.707 of V peak. And again, the 1 over square root of 2 is the more accurate. This is an approximation, of course, it's rounded. But somehow, for myself, I find it easier just to memorize these numbers, the 2 over pi and the 1 over the square root of 2. I don't know that I have those reliably memorized. But the numbers roll off your tongue, out of your brain pretty quickly here if you've used them a lot. So 0.707 is going to be our RMS. And so it sits a little higher than the average. Sits in around here. Okay. The RMS value of a sine wave. Okay. Okay, and of course, I mean, well, we have peak there, you know, and there's the peak to peak. We're not, the peaks are going to be symmetrical, about 0 volts. We're not going to be doing problems with sine waves with offset, maybe very much at all. The book does not, like I say, the book does not address it. But so we have our peak voltage here. Of course, peak to peak is another parameter we could do, right? Just making sure we got them all. That is the period, right? And then again that. So again, I think we've got them kind of mapped out here. It's again, it's the nature of the beast. It's we've got voltage changing in time, so now we have to deal with waveforms and all the parameters that we need to describe the waveform. And I think that's all of them. Instantaneous, yeah. Okay. I do have some handouts that I'll post that also sort of summarize this. They kind of help you keep it straight, like what parameters belong to what waves. Like we mentioned, you know, pulse width, space width, obviously that's only rectangular waveforms. And now these new ones here, like phase angle, obviously that's only pertains to sine waves. And it's the one that makes you sound cool when you talk. Say phase angle a lot. Hey, that's not the end of it. In the AC course, we're going to be doing vectors and phasor diagrams, and oh yeah, it gets impressive. So, and then you're using those words because you really need them. So you can sound smart, but you also they're just actually necessary now. But yeah, so we've got these parameters sketched out for ourselves, and then we'll just get practice using them. Again, what you can do to sort of get started on some practice with getting comfortable with these parameters and how to measure them. Again, create a sine wave in the analog discovery and then fly it into your scope, you know, connect your scope channel to the output of the wave generator. Bring it in and you can get practice dialing it in with your scope, right? Like you need the triggering settings and the scaling. And then you can get the cursors out and you can measure things with the cursors. You can measure certain times. You could look for instantaneous voltages and you could get some practice doing that. That'd be great practice. You could look for a point on that sine wave and measure the time with vertical cursors off of 0 here, right? So at what time does that point occur that you're looking at out of the total time, right? Then use this formula. And then you get the phase angle here. Take the sine of it with your calculator times V peak. You can now calculate what you would expect to see as your voltage that's sitting here, and you can get that voltage with cursors too. So just putting up a sine wave in your scope on analog discovery and sort of moving around with cursors to measure time and calculate instantaneous voltage, and also then measure that voltage with your scope cursors to double check yourself. That's really good practice. Yeah. And just even measuring time with scope cursors and converting it to phase angle like we did here. You know, like when we said we were looking at 0.4 milliseconds out of a 4 millisecond cycle time, and we just get used to doing this. You know, the 36 degrees is the angle. The phase angle, that kind of stuff you can practice because that's going to be really big. We're going to be measuring phase angles a whole lot in the AC course, so it just help you get oriented with that. So again, you can break out your analog discovery and just work on those kinds of things. I will post, like I said, some summary sheets that you can look over in the in week 2 under files. Let's see, some of them, don't be intimidated. I'm debating if I should post the whole thing. I guess I'll post the whole thing. I'll see. Some of it looks a little intimidating, but we'll see. At least then we have it. It's not something that we're going to memorize all of it, but as a reference sheet, it's not bad. So, okay, that'll do it for now.